We started on Friday talking about solutions to the Laplace equation, and we related this. We started to see the relationship between solutions to this differential equation of second order and analytic functions, right? Which are this nice class of complex functions that are it's quite strong, the condition of analyticity, as we started to see. Yeah?
Just a quick question. I was on Wikipedia and whatnot, and I was confused because I saw functions being referred to as both holomorphic and analytic. Is there any difference we should know about? Or we can use?
The difference is historical. It turns out they're the same class of functions.
Okay.
It's exactly the same, but it wasn't known for some time. Those two terms converged, that is to say. They described different things, and then it was realized that they are in fact the same thing. We'll discuss that in chapter 5, when we talk about Taylor series and Laurent series, which are Taylor series but with rational functions instead of just polynomials. Okay? Yeah, good question. I was actually reading about that semi-recently myself, and yeah, it's one of those funny historical things that we will talk about that. Okay, good. So I told you this theorem last time, right? And we didn't prove it. We'll give a sketch here now. So if we have some function f of z given by u of xy plus I times v of xy, which is analytic in D, in domain, I should say. Then each of our real value functions is harmonic in D. I might have skipped this in our recap, but remember, harmonic just means a solution to the Laplace equation. Okay? So, this is just recapping still. I told you this, right? This relies on a lemma, which we'll prove in a few weeks, but I'm just going to use it now. If f of z is analytic, in D, then our component functions u and v have partial derivatives of all orders. Oh, sorry. Of all orders. Furthermore, which are continuous. Just for emphasis, we put that there. So we'll prove that in a couple weeks. Right. So, then I refer to this thing by Clairaut's theorem. Which is just the familiar fact from calculus 3 that mixed partials can be taken in any order. Okay? We have that the second partial of u with respect to y, just to remind you, this is what Clairaut's theorem says. We can differentiate with respect to y in either order. by Clairaut's theorem and by the Cauchy-Riemann equations, we can make the following computation. d dy of du dx is just equal to d dy of dv dy, right? That's one of the Cauchy-Riemann equations. We get d squared v dy squared. Now, this is the second equality that I'm writing vertically is by Clairaut's theorem. This is the same as d dx of du dy. Okay, and then this equality comes from the second Cauchy-Riemann equation I'm about to write. So we get d dx of negative dv dx, or in the end, we get d squared v dx squared times negative 1. Okay, so we have equality here as well. So what does this tell us? D squared v dx squared plus d squared v dy squared is equal to 0. So v is harmonic. Okay? So I'll leave it to you to make a similar computation. For u. I'll leave the box open since I didn't show you all the computations and we didn't prove that lemma. Okay? So this is cool. Okay, this is kind of mentioned this. It's like, oh, it turns out in physics, solutions to the Laplace equation are all over the place. They arise in a lot of seemingly disparate physical situations. And in light of this result, maybe it's not really that surprising, right? Because analytic functions are kind of a very useful or ever-present class of functions, right? Anywhere there's a complex situation lurking behind some physical situation, it makes sense that you might get a solution to the Laplace equation popping out. Okay? So, here's the question. Can we go in the opposite direction? Given a harmonic function, can we construct a partner for it to get a complex analytic function? Okay? So, conversely, given u of xy, harmonic in an open disk, let's tell you outright, we can, in fact, construct a function, I should say, harmonic function in that same disk. With a harmonic function, sorry, I should call it something, v of x comma y plus I times v of x comma y analytic in the disk. Okay, let's do this in a particular case. Let me just add a piece of terminology here. We call v of x comma y the harmonic conjugate. Of u of x, y. Now, of course, again, we encounter overloaded terminology. Yeah?
So would f of z equals v of xy plus I u of xy be another analytic function?
Sure, yeah, you're just multiplying by I, right?
Yeah.
So, you know, we haven't proved this, but multiplications, additions, and compositions of analytic functions are also analytic. I mean, we did kind of express that, right? Because we said that the usual rules of differentiation apply.
Yeah.
So you can take the few extra steps to show that that implies you can do that for analyticity as well. Okay, so yeah, yes is the answer. So again, sorry for this overloaded terminology. Conjugate, right? This means something very specific to us in complex numbers, right? But here, you know, we're talking about real valued functions, so there's no conjugation in the usual sense going on, right? So sorry. Okay, so for example, let's construct an analytic function whose real part is u of xy is just the polynomial in two variables, x cubed minus 3xy squared plus y. Okay, so how do we proceed here? Well,
Do we need to show that u of xy is?
yeah, that's a great place to start. We should verify that this function I gave you is in fact harmonic, so that we can find the harmonic conjugate, right? Okay, so first, u of xy is harmonic. Okay, so what do we do here? First, the partial derivative of u with respect to x is what?
X squared minus 3y squared.
Yep. Good. And then let's iterate that differentiation. What do we get here when we take the derivative with respect to x again?
6x.
Just 6x. Good. Okay. How about the first derivative of u with respect to y? We get here.
Negative 6xy plus 1.
Negative 6xy plus 1. Good. And now the second partial of u with respect to y. Let's get negative 6x, right? So you see here that the second partials just differ by a sign. So that's satisfying of the Laplace equation. In fact, where is this function harmonic? Yeah.
when it's 0 or equal to 0?
So yes, when I add these two, and I get 0, that's right. And that happens everywhere. That for every point in the complex plane, we satisfy the Laplace equation. So in fact, we're harmonic in all the complex numbers. Okay. So then let's look at what the Cauchy-Riemann equations tell us. Then the Cauchy-Riemann equations tell us that partial v partial y is equal to partial u partial x. That is 3x squared minus 3y squared. And partial v partial x equal to negative partial u partial y is just equal to 6xy minus 1. Yeah. Okay. That is to say, we want to find a v that satisfies these equations. Right? That's what we're looking for. The harmonic conjugate of u of xy. Okay. So that is to say, these, I'm just pulling right from here. And I'm looking for the u that satisfies both these equations. Okay. So, I'll calculate the indefinite integral of partial v partial y with respect to y. Okay? So that is to say, what is the antiderivative of this function here with respect to y?
3xy squared plus y cubed, or sorry, minus y cubed plus the function x.
Yeah, exactly. So we got 3x squared y minus y cubed plus c of x. Of course, remember this from multivariable calculus. We have to add a constant when we take an indefinite integral. But when we're just considering the variable y, any function of just x is treated as a constant. So we throw in this whole constant c of, function as our constant, c of x. Okay? Good. So, I should remind us that this is some expression for v of xy. And now I'll differentiate this expression that I have here for v of xi with respect to x. Partial v partial x is just equal to 6xy plus c prime of x, right? Again, our constant function, our function of x is constant with respect to y, but we can differentiate it with respect to x. Okay? Now, we compare this with what we insist that the partial of v with respect to x is. We can equate these things, right? So, this is in fact equal to 6xy, minus 1. Okay, so, this tells us that c prime of x, the derivative of c of x, is equal to -1. which tells us that the antiderivative of c prime of x dx is just negative x, right? Plus a constant. This time a real constant. I'm sorry, an actual constant, right? Not a constant which is a function of unconsidered variable. Okay? Okay, so we can stop here, right? This implies that v of x comma y is some function of the form 3x squared y minus y cubed minus x plus a or some constant, a real number, right? That is to say, the harmonic conjugate is not unique. It's just like a general antiderivative or indefinite integral, right? It's a whole family of functions that serve as a harmonic conjugate for a given function. So any choice of a will do. Okay, so I guess my terminology was a little ambiguous, right? I said the harmonic conjugate, but really what I mean is that there are many functions that satisfy. You can construct an analytic function on a given harmonic function. Okay, so just to give a complete solution here, right? Our analytic function f of z is given by x cubed minus 3x y squared plus y plus I times 3x squared y minus y cubed, minus x plus a for any a is entire, right? This is analytic in the whole plane, because remember, we found that u was harmonic in all of C. Or, yeah.
So,
Right, you see what I mean here by C, right? I mean pairs x comma y that come from complex numbers. So I shouldn't say this actually, I'll just put this as R2. Yeah.
So just a question, does this work for any, like, I guess I'm a bit confused, for a u of x that is harmonic,
Mm-hmm.
would any other harmonic v of x work? For construct an analytic f of c?
No, you have to make sure that they satisfy the Cauchy-Riemann equations. Remember, because that's what our effective condition for checking analyticity is.
Because I was confused, like, why not just multiply u by a number, have a new analytic function?
Because then you wouldn't satisfy the Cauchy-Riemann equations. Yeah.
so
Good question.
is f of z always analytic where u is harmonic?
Yes. Yeah. Of course, you'll notice the change in
Yeah,
terminology,
yeah.
but we're only concerned with the topology, the topological aspects of the plane.
So whatever shape that's harmonic on the same shape in the complex plane is where it's analytic?
Yeah, exactly. Right. Right. That is to say that the real plane and the complex plane are homeomorphic. They're the same topological space. But remember, it's the multiplicative structure that distinguishes the complex plane from the real plane. Okay? Yeah. That's a subtle point. I'm sorry that I misled you at first here by writing C. Okay. So, in fact, this same procedure necessarily always works for U harmonic in an open disk for the entire plane. And maybe there'll be a homework about showing that can fail if you're harmonic in some other type of region. I'll think about that. Maybe that'll be on the next problem set. Okay. Right. So this really this is kind of like the converse. This is the other half of the theorem that we proved at the beginning of class, right? And that is, every analytic function gives rise to two harmonic functions, and now, given a harmonic function, we can construct an analytic function. Okay, so we can go both ways. So let's see what we can do with this. We're going to talk, this is probably the last time for quite a while that we'll talk about any differential equations. But let's talk about some applications of this connection that we've just drawn to differential equations. Okay. So let me remind you of some things from multivariable calculus. So given a real value function, phi of x comma y, the level curves of phi. Everybody okay with this? The Greek letter phi? Probably seen that before, right? Yeah. Okay, good. The level curves of phi are the family of curves given by setting the function equal to a constant. Right, that is to say, take some real number c and set my function equal to that, and I look at the set of points in the plane that satisfy this equation after choosing a c. I feel obliged to give you the same talk that I gave my Calculus 3 students a couple weeks ago. The graph of phi is a two-dimensional thing sitting in three-dimensional space, right? It's a surface of some kind. And then what we're doing by considering a level curve is we're picking a z value to slice that surface along. And where the plane that's parallel to the xy plane slices through our surface is the curve that we get by this equation. Okay? So, like, what do we have here? Like, this is great. I wish we had these chairs in my Calculus 3 class. This is like a saddle, right? It has a saddle point. It's concave down this way and concave up this way. Right? So what happens when I take a plane and I slice here? Let's pretend my book extends infinitely. I get a hyperbola, right? And then as I move down, if I go from the underside, I slice and I get a hyperbola this way, right? Those are the level curves of this surface, okay? Okay, so as you might guess, we'll study the level curves of the real and imaginary parts of an analytic function. Let's see if there's anything useful or interesting we can say. For example, let me give you an equation of the back of this chair. That is, let me consider f of z given by z squared. We actually made this computation a bunch already. What do I get for my real and imaginary components? I get x squared minus y squared for my real component, plus I times 2xy. Okay, so my real component function is the equation of the back of this chair, the saddle. Okay, so let's draw the level sets, some level sets for both of these functions. Okay. Some level curves of x squared minus y squared. Okay, well, I mean, that is to say, if you believe that demonstration I just made, we're just going to have a bunch of hyperbola on the plane, right? Can't draw a hyperbola without an asymptote or a pair of asymptotes, right? Okay, so oh, that's terrible, sorry. Here's the level set. Real part of f of z is equal to 1. Okay. Oh, sorry, I didn't draw the other half of it. Okay. I got a shallower hyperbola at the real part of f of z is equal to 2, right? And then, remember, as I lowered myself in the z-axis, became negative, the orientation of my hyperbola flipped from one opening this way to one opening this way. Okay, so this is my level curve at the real part of f of z equal to -1, right? Same story here. I just get a slightly shallower hyperbola at the real part of f of z equal to -2. Sorry, -2. Okay. Just one thing to point out here. I don't know if we'll actually come back to this, but what's the level set at the real part of f of z is equal to 0? What level curve do I get there?
Wouldn't you get the asymptotes?
Yeah, exactly. Right, you just get the pair of lines with slope -1 and 1. That is to say, interesting phenomenon here, right? We have, this is clearly a continuous and differentiable function. But note that when you look at the level set of this function at 0, you get something which is singular at the point 0, non-differentiable. It's kind of interesting. We might say more about that, but not necessarily. Okay? So let's do the same type of picture for the imaginary component. Okay? So sorry. Should label this properly. Some level curves of Why? What's the graph of this function look like in general? Yeah, it's another class of hyperbola, right? When I set this equal to a constant, I get another collection of hyperbola, okay? That is to say, here, now my asymptotes are the axes. Oh, sorry. Really bad. It's kind of silly, but I find it easier to start from the middle when I'm approaching two asymptotes. Okay, let me try to not do it that way. I do it okay, I guess. So, in other words, what do we have here? The imaginary part of f of z here is equal to 1. That's this curve, this inside one. And then, same story. This outside one is the imaginary part of f of z equal to 2, right? This and this together, the outside ones. And the inside ones is where the imaginary part of f of z is equal to 1. What happens when I go negative here? Yeah, I go the other way, right? Right, so I get the imaginary part of f of z equal to -1, and just for completeness, let's draw one more here. Same story. The imaginary part of f of z is -2. Sorry, equal to 2. Okay, so what I would like to ask you to do is to imagine these two pictures superimposed on one another. The two graphs, or the two families of graphs that I have here on the left-hand board. Imagine placing one on top of the other. And if you can't do that easily, I'll ask you to look at page 82 of the textbook. I draw it nicely there. What happens, or what appears to happen when you superimpose these two pictures, is that the level sets of the imaginary part intersect the level curves of the real part at right angles, is what it appears. Okay? Not only do I not want to redraw this, but my drawing is so crappy that it wouldn't be apparent that they're at right angles. But look at the book, it really does look like they're at right angles. And in fact, they are. Okay? So, right. So let's prove that.
I just pulled it up on my, here, I have it right here.
Oh, great.
Yeah.
Yeah,
I can't really zoom in for some reason, but this is what it looks like right here, if
yeah,
anyone can see it.
that top one, yeah, that's,
Yeah, this top one.
that's exactly, thank you for that. You know, if I was more technology able, I would have had a digital copy of the textbook on this computer, but thank you for that. Good. Right, so, let's prove this. The intersection of the level curves of U and V are always at right angles. Unless f of z is equal to 0. Anybody remember from calculus 3 what you call it when a function is differentiable and not equal to 0 at a point? It's kind of an important condition. It's stronger than differentiability because you're requiring it to not vanish. This is really important if you took differential geometry or plan on taking it. You'll study this class of functions a lot. It's called regular. A function is called regular when it is differentiable and not equal to 0 at a point. So, look back at our example, right? What would happen if the derivative were 0 at some point? This is related to how our level sets become singular when we're equal to 0. Okay? Think about that. Maybe I'll incorporate that in the next problem set as well. Some thought about that. Think about that for a little bit. Okay? But for now, let's just go ahead and prove this. Okay? Right. Oh, I guess here's another way to say this. Level curves of harmonic conjugates are normal. Kind of the catchphrase there. Okay. So, okay, remember the gradient? The vector of partial derivatives, right? Which we denote in the following way. What do you guys call this symbol?
Del.
Nabla is the classical one. Del is becoming more popular. I like that better. This is called Nabla because that's a type of ancient Greek harp. That's what this symbol is supposed to be. I think that's so ridiculous. But yeah, anyway. Nabla V xy is just the two-dimensional vector dv dx dv dy. Okay. So the gradient vector is always normal to level curves. You guys remember this from calculus 3? So if I want to, say for example, if I want to define the tangent line to this level curve when r of f of z is equal to 2 at this point, 2 comma 0, how do I do that? How do I specify the tangent line to this curve at this point? Anybody remember that? Okay, so
Tangent line.
tangent line, yeah.
You just take the derivative point onto the point.
Yeah, that's completely correct. However, if we want to generalize that to arbitrary dimensions, what we do is we take the gradient vector, which points in this direction, and look at the vector that's perpendicular to the gradient vector. Right? So, and then we parameterize our line by it going through this point and having a vector parallel to it that's orthogonal to the gradient. And that's kind of the motivation for the gradient is always normal to level curves. That's how we use it to define the tangent line, plane, set for arbitrary dimensions. Okay? Okay. So, right. So let me just outline the strategy of what we're going to do here. we know that each of these gradient vectors is normal, perpendicular to each of my level curves of u and v respectively. So that means if I can show that these two vectors are perpendicular, then the curves themselves must be perpendicular at each point, right? Is that okay?
Yeah, if you use the Cauchy-Riemann equations.
Exactly. That's what we'll do. We'll take the dot product of these two gradient vectors, use the Cauchy-Riemann equations to show that in fact it must be 0. Okay. So let me write that down. If the gradient of u and the gradient of v are perpendicular, then so must the curves be. Okay. All we have to do is calculate a dot product. Check that it's 0. Okay, so let's proceed. Okay, what do we get? We get du dx dv dx plus du dy dv dy, right? And of course we can just substitute. For example, I'll put negative dv dx in for du dy and dv dy in for du dx, right? Dv dy dv dx minus dv dx dv dy. Find the CR equations. Okay. Right. Yeah. So. Let me just reiterate this. The condition f prime of z not be equal to 0 is equivalent to insisting that the gradient of u at x, y is not equal to 0 vector, and the gradient of v with respect to x and y, again, is not equal to the 0 vector, right? Because if either of them were equal to the 0 vector, we wouldn't get any information out of this dot product. It would automatically be 0, and it's not meaningful to say anything about perpendicularity then. Okay, just a reminder, i.e. u and v are regular at the point x comma y. That is, their gradients are non-zero. Okay. Okay. So this is a useful result because we can solve now the Laplace equation in a region that has a boundary given by level curves of some harmonic function. Okay, so this kind of broadens the possibility of solving a boundary value problem in 2 dimensions. We can recognize the boundary of our region as level curves of some harmonic function. Okay, so let's do a quick example. So let me ask you to find a harmonic function p of x comma y in the region in the positive real half plane between curves x squared minus y squared is equal to 2, and x squared minus y squared is equal to 4. Now I'll tell you the boundary conditions. This function phi, taking the value, three on the left, and 7 on the right. Okay, let me draw you a picture. This is not an easy thing to say in a clear way with just words. Show you the region that we're looking at. So, okay, so I'm kind of looking at this whole infinite region here, right? It thins out a lot as we approach the asymptote. Okay, here's my level curve. X squared minus y squared is equal to 4. Here's my level curve. X squared minus y squared is equal to 2. And our boundary conditions are telling us that we want our function phi equal to 3 for all points along this curve. Every point in the plane that lies on this bounding curve should have output phi equal to 3. When you plug in a point here into phi, you get 3. Okay.
What is the interval that you're marking on the x-axis?
So this is just this is where this curve intersects the x-axis, right? When
root 2.
yeah. So let's see. Should be root 2, huh? Yeah, you're right. My tick marks are meaningless here. Sorry. This intersects the x-axis somewhere. The general picture is right, though. You know. Thank you for pointing that out. just so we have a shallower thing here, and a curvier thing on the left, sorry. Okay, right, so and on our right curve, we want phi to be equal to 7 for every point along this curve. When we put it into phi, we get the value 7. Okay, so we recognize x squared minus y squared, of course, as the real part of z squared. Implies the boundary curves are harmonic level sets. Okay. So to satisfy our boundary conditions, let's just let A and B be real numbers. Okay? And set phi of xy be equal to A times x squared minus y squared plus B. Okay? So then whenever we have x squared minus y squared equal to 2, right? That is to say, along this curve, we get phi of xy is equal to 2a plus b. And when x squared minus y squared is equal to 7, i.e. along our, equal to 4, sorry, that is our right bounding curve, we get phi of x comma y is equal to 4a plus b is equal to 7. Okay, so just solve this pair of two equations and two unknowns. And what do you get? You get a is equal to 2 and b is equal to -1. Okay, so altogether, this tells us our function phi satisfying the harmonic equation in our region is given as follows. Okay, so this is kind of contrived, right? This is just like the example that we've been working with a lot. Might seem kind of trivial or not that interesting, but we'll come back to this much later, closer to the end of the term, and do something maybe more interesting with these types of regions bounded by harmonic level sets. Okay, just wanted to show you that now in a simple case. Yeah.
So the way we constructed the solution, there was nothing to guarantee that it would be harmonic. Right? It was just like a guess. Or...
Yeah. So we know that this is harmonic just because our complex function is analytic. Right? That's a real part of it. How did I come up with this solution? Yeah. How do we solve differential equations? Yes. A lot of times, unfortunately, is but we'll say more about this back in chapter 7, I think. Yeah. So we'll approach this in a more systematic way a little later. But for now, just know that this works. Okay. Yeah, that is something really frustrating about differential equations, you know. There's very little that you can do systematically. There are only a few types of differential equations that can actually really do anything with, right? That's been my experience, at least. Okay, so let's accordingly move away from differential equations for a while. I want to talk to you about Julia and Mandelbrot sets. Okay, so I want to talk about a particular class of complex sequences, and we'll try to do some systematic study of this class of sequences that I'll introduce now. Okay, so the definition. Given a complex function, f, and some complex numbers e naught, then the sequence given by z naught, f of z naught. Actually, let me call this z1, which is just equal to f of z naught. Z2, which is equal to f of z1, or f of z naught. So on and so forth, right? I'll just keep applying f again to the output of my previous step. Okay. The sequence of the second is called an orbit of the function f in C. With seed z naught, the initial input, this complex number z naught that I picked at the outset. Okay, so let's keep working with this same function we've been working with all day. For example, let's take f of z again equal to z squared. Then what can we say? With seed z naught, then one thing we can say is if the modulus of z naught is strictly less than 1, the orbit of f that is bounded. And converges to 0. Right? That is to say, the limit as Zn approaches infinity, sorry, not Zn, as n approaches infinity, Zn is equal to 0. This makes some kind of intuitive sense, right? If we take something with modulus less than 1 and keep squaring it and squaring it and squaring it, getting smaller and smaller and smaller, right? Okay. While if the modulus of Z naught is strictly greater than 1, the orbit is unbounded. Right? That also makes intuitive sense, right? I take something larger than 1 and keep squaring and squaring and squaring, it's just going to get larger and larger. So, in general, here's the theorem. Kind of based on our observations. So, if f of c is analytic in a neighborhood of our favorite letter zeta, so z equals zeta, with f of zeta equal to zeta, and the modulus of the derivative of f evaluated at zeta is strictly less than 1, then there's an open disk. An open disk around zeta so that all points in the disk we say launch orbits which stay in the disk and converge to zeta. Okay. So when I say all points in this launch orbits, what I mean is that if you take any point inside this disk and make it the seed of an orbit, it will stay inside this disk and converge to this point, zeta. Okay, so this is just like what I'm saying for our example, right? Z squared is analytic in a neighborhood of 0, and 0 squared is equal to 0, and we have that the derivative is strictly less than 1, it's 0, right, when you evaluate it at 0. So in the open ball, the open ball of radius 1, anything will converge to 0 when you build an orbit out of it. Yeah?
When you say f prime zeta, is that the derivative of f with respect to z?
Yeah, yeah.
Okay.
Which we know exists by the analysis. Good.
And is it really just as easy as like the derivative of like z squared? Vector z is 2z.
Yeah,
Okay.
yeah. We discussed that, right? Didn't we discuss that? I think so. Like when we gave the definition of differentiability, taking the derivative of a polynomial, all the derivatives are the same that we've discussed so far, polynomials, exponentials. We haven't discussed trig functions or logs yet, but we'll do that Friday. Start doing that Friday. But yeah, so for polynomials, the same old rules for differentiability apply.
So is there a specific way to determine what the open distance around zeta?
Well, kind of have to go on a case-by-case basis.
Okay.
Maybe in the course of the proof, we'll have something illuminating to that question. Okay. So, let's prove this. So we have the derivative z approaches zeta of the modulus it's a zeta is equal to this is part of our hypothesis, right? That the modulus of the derivative at the point is strictly less than 1. And this kind of, Joseph, this addresses your question to a certain degree, right? We're not, in the case of polynomials, yes, you can differentiate as normal, but for the general proof, we're just appealing to the definition of the derivative. Okay. Good. So, and the other part of our hypothesis that we'll use right away is that f of zeta equals zeta. Okay? This implies we can find rho, a real number, between the modulus of the derivative of f at zeta and 1, satisfying the following. F of z minus f of zeta, the modulus of this, which is just equal to the modulus of f of z minus zeta, right? I'm just using my hypothesis here of equality, is less than or equal to rho times v minus zeta. Okay, all I've done is pick some real number between here and split my modulus function across the two factors of my numerator and denominator and multiply the denominator to the other side. That's all I've done. Okay? This is to say, for suitable, for z in a neighborhood around zeta. Okay. So then what we want to do then consider the orbit you can say seeded by Z naught in this neighborhood. Okay, so just let's write this out explicitly, right? First we get Z, then we get Z1, f of Z naught, Z2 to f of Z1. Okay, so what we have is the following string of inequalities. Zn, the modulus of Zn minus zeta is less than or equal to rho times the modulus of Zn minus 1 minus zeta less than or equal to rho squared times the modulus of Z to the n minus 2 minus zeta. This goes on until I get down to rho raised to the n power times the modulus of Z naught minus zeta. Okay, so remember, we found rho such that it was less than 1. No? So, since rho is less than 1, Z sub n is closer to zeta than Z sub n minus 1. So, we converge to zeta. That is, our orbit converges to zeta. Okay. Great. So, here's some terminology associated with this construction and this theorem. Zeta is a fixed point of f if we have zeta as in the theorem. F of zeta is equal to zeta. Right? It's kind of an intuitive definition. Okay. A fixed point satisfying the theorem is called an attractor. precedes whose orbits converge to zeta is called the basin of attraction. This is, again, I know I said we were stepping away from differential equations, but this is kind of like when you study sinks and sources in solutions of differential equations in phase space. If you don't know what I'm talking about, that's fine, it's not really relevant to what we're going to do. But there's a similarity here. These definitions are all you need to know for what our purpose is. Okay. Right. So back in our first example, right, for f of z is equal to z squared. We have an attractor at 0 with basin of attraction. The unit is the open unit is. Sorry. Okay. So one more definition to add here. So let's see. If zeta is a fixed point of f with the modulus of the derivative at zeta strictly greater than 1, zeta is a repeller of f. Sorry. Okay, so again, returning to our example of z squared, are there any repellers in for f?
Everything with modulus strictly greater than.
So remember, you have to be a fixed point to be a repeller.
Oh, right. So,
First of all, does it have any other fixed points besides 0? What complex number?
Wouldn't it be any with modulus 1 also?
Well, remember, arguments add when you multiply things. So anything with a positive, with a non-zero argument, I should say.
so specifically the point 1.
Just one, yeah. The only fixed points of the function f equals z squared are 0 and 1. What's the derivative of f at 1? What's the modulus of the derivative of f at 1? It's just 2, yeah. So it's a repeller. Yeah, exactly. So f of z equals z squared has a repeller at zeta equal 1. Okay, so
What does it mean for something to be a repeller? Because like an attractor means that everything inside of a certain basin like converges to it. Does a repeller have like a similar idea of like everything in a certain area diverges or goes away from it or anything like that?
So, I think it's more useful to just think of it as not an attractor.
So it's a fixed point that's not an attractor.
Yeah, that's
Okay.
really the useful, because it doesn't have such an easily characterized interpretation. Yeah. Okay, so I want to continue with this example of z squared. We talked about things with modulus strictly less than 1 and modulus strictly greater than 1. What about the things of modulus 1? Well, here's one complex number with modulus 1. What about all the other complex numbers with modulus 1? What orbits do they launch for the function f of z equals z squared?
Oh, circle.
Yeah, they just stay on the circle, but
They stay on the circle. Yeah.
Do they each only go to certain points on the circle?
Ah, that's a very good question.
Does that have to do with like the primitive roots of unity or something like that, where like some of them can span, some of them.
Okay.
Right, so they have to stay.
Sorry, what was that last part?
You double the argument, right? So
Okay, yeah, so, we know that, primitive roots nth roots of unity for any m are complex numbers with modulus 1. Let's look at what happens, when we consider some of those. Okay, let's let z naught, our seed, be, in particular, a primitive cubic root of unity. Yeah? Okay? So then, z1 is equal to e to the I 4 pi divided by 3. Right? Okay? Z sub 2, what do I get? I get e to the 8 pi over 3, which of course is equal to e to the I times 2 pi over 3 times e to the I 6 pi over 3, which is just 1, right? Because 6 pi over 3 is just 2 pi. Over 3. Ended up back where we started. Right? And if I if I put z naught back into f, what do I get? Just z1 again. And so I just I go in a 2 cycle. Call this orbit a 2 cycle. Which has period 2. Okay.
Why does it have period 2?
Because 2 is the minimum amount of times you have to iterate for it to repeat.
Okay, different question. Then why is it called a 2 cycle? Is that not the same?
So for 2, it's trivial, right? What if you have like you could have a 6 cycle with period 3. The period has to divide whatever the cycle is, right? You might have a cycle that has 2 copies of a smaller cycle inside. So the period of a cycle is the first time that it repeats itself. So for 2, it is kind of redundant, but the general term is, we say that anyway because you can talk about the period of any n cycle. It has to be a divisor of n. Okay, good. So think about this also. Note that the seed e to the I 2 pi over 7 launches an orbit which is a 3 cycle. And the seed, e to the I 2 pi divided by 15, launches a 4 cycle. Okay, kind of interesting. We're just putting these up at random. So I'll ask you to, in the next homework assignment, to discern some pattern out of this and prove that it always, that whatever you conjecture always generates an n cycle. Okay? So, by contrast, if we take a real number alpha, which is irrational, the seed e to the I alpha 2 pi never repeats. That is to say, what do I want to say here? That it kind of fills the unit circle. Right? Technically, we say something that the orbit is dense in the unit circle. Okay, that is to say, precisely what we say is that every point in the unit circle has infinitely many arbitrarily close points that are in the orbit of this seed. Okay, slightly weaker than saying it fills the unit circle, but some more topology that we won't really get into. But I'll also ask you about this on the homework. Start thinking about that now. Okay. We're doing on time. Okay, we're almost to a great spot. Okay, so we want to kind of classify our orbits, right, in terms of boundedness or non-boundedness. Okay, so needless to say, these are all bounded, right? All these examples here, ones that stay on the inner circle, but they don't converge anything, right? So we have the basin of attraction for zeta equals 0 is the open ball of radius 1. Then we have these bounded orbits that lie on the unit circle but don't converge. And then we have the unbounded orbits which don't converge. So we want to kind of be able to make this type of classification for arbitrary polynomials. Let's just start with. Okay? Okay, so. Filled Julia set. Or a polynomial function. F of z is the set of points that want bounded orbits or F. And then we call the Julia set, not necessarily filled. Is the boundary of the filled Julia set. Okay. Right. So, in our motivating example, d squared, what is the Julia set?
Modulus of z is less than or equal to 1.
That's the filled Julia set, yeah. Good.
Oh, so just equal to 1 would be the Julia So.
Yeah, exactly. So the filled Julia set is the closed unit disk, and the Julia set is just the unit circle. Okay, so let's record that. For f of z equals z squared. Filled Julia set is the closed unit circle, unit disk, sorry. And the Julia set is the unit circle. Okay, really quickly, I think this might be the last thing we have to do today. Let's look at a different example. So, let's let f of z now equal z squared minus 2. Okay, so what's the filled Julia set of this function? Let me tell you. Do you have a guess?
Like circle and radius 1 around -2, 0.
This is a little degenerate, actually. So let's see what happens here. The filled Julia set is given by the real interval, -2, 2. Viewed as a subset of C, right? Just a little chunk of the real axis is the filled Julia set for this. Let's see why. Or I'll give you some justification. I'll show you that every orbit launched from within this interval is bounded. It's a lot harder to show that anything outside that interval, any other complex number, results in an unbounded orbit. If we have time, we'll get back to that in chapter 7. Okay? It's actually quite complicated. But I'll at least convince you that this is all these points launch bounded orbits for this f. Okay? So, right. For real number x, satisfying the necessary inequalities, then we know that x squared is between 0 and 4, right? Okay, so this implies that we can note the following, that -2 is less than or equal to x squared minus 2 is less, which is equal to f of x is less than or equal to 2. Okay? So there you have it. If I start with something in the interval 2 to 2, I get, again, something in the interval 2 to 2 as an output when I put it into f. Right? Okay? Right, so oh, sorry. Well, one question here. What is the Julia set of f? If you believe me for a month or so that this is in fact the filled Julia set, what's the Julia set? line.
So it's the same.
They're the same thing, exactly. Every point of this as a subset of the complex numbers is part of the boundary, right? Because every neighborhood I take around any point in here will have points both in the set and out of the set. Now, here's what I want you to think about for Friday. What are the Phil Julia sets for something of this form? C is any complex number. Okay, I mean, we've done two cases, right? 0 and -2. And we got a circle and a chunk of a line. So, well, maybe it's like, kind of like stereographic projection, where circles and lines are the things at hand. Or maybe it's completely different. I guess we'll find out on Friday.
So for something bounded, does the codomain of f of z naught have to be a subset of the? Like, see that?
Yeah, I'm sorry.
Yeah, no, I don't think that made much sense, but that's not what I was trying to say. I just don't know how to say it. Like, when you take f of z naught, it equals to, z1, and then that, when put back into f, has to like stay in the same general area. Because if it ever like,
Yeah, right. So this is, think back to our example of z squared, right? Like, you won't have it that something in the basin of attraction of 0 jumps outside.
right?
So yeah, it has to, there is like some area which it can't go outside of, right? For it to converge.
Thank you.
Yeah,
Thank you.
yeah. See you Friday. I really wanted to get to.
Is the
When's the next work session?